Dr. Aruna. I am going to handle analysis of indeterminate structure. So first we will see about the introduction. So what do you mean by structure? Structure means consists of number of elements. So for example, slab, beam, foundation, wall, all those things comes under one structure. Consist of number of elements. That is called as structure. Next one, structural analysis. We are going to study about the structural analysis. Okay, what do you mean by, what is the use of structural analysis? So the main purpose of structural analysis is to predict the response of the structure when the structure is subjected to external load. That response may be shear force, bending moment, stress, strain, all those things. So next one, types of supports. So the supports give the stable to the structure. It provides stability and strength to the structure. So basically three types of supports are available. The first one is roller support and second one is fixed support. Third one is pinned support or hinged support. Now coming to roller support has one support reaction. So that support reaction along vertical direction. So which means it does not allow any vertical movement, along the vertical direction. Okay, it allows only the rotation and horizontal movement. So number of support reactions of the roller support is 1. So skating is the example of the roller support. Next one is hinged support. It is also called as pinned support. So this diagram, this symbol represents the pinned support. So it has two support reactions. One is along the vertical direction, another one is along the horizontal direction. So which means it does not allow any vertical movement as well as the horizontal movement. It allows only the rotation. Examples, doors and windows. So next coming to the third support, that is the fixed support. So fixed support has three support reaction. So one is along vertical direction, another one is along horizontal direction, another one is rotation. So the total number of support reactions of the fixed support is 3. So the example is, here one pole is connected to the concrete block by bolted connection. This is rigid jointed and fixed support one. So next one is types of loads. So three types of loads are there. The first one is point load or concentrated load. So it acts at only one point. So this point, this point, this point. So it is called as point load or concentrated load. The unit of the point load is kilonewton or newton. So next one is uniformly distributed load. UDL load. It is also called as UDL load. The intensity of the load is constant over entire the span of the beam. Now coming to the uniformly varying load. So here the intensity of the load is varying at each and every cross section. So before solving the problem, we have to convert this UDL load into point load as well as UVL load into point load. So that point load acts at the CG of this UDL and CG of this triangular load. The unit of this UDL load is Newton per meter or kilonewton per meter. Here also the unit of uniformly varying load is Newton per meter or kilonewton per meter. So next one is types of structures. Basically two types of structures are there. The first one is statically determinate structure. Another one is statically indeterminate structure. So statically indeterminate structure is very stable compared to the statically determinate structure, because statically indeterminate structures having more number of support reaction. So how we will identify whether this structure comes under statically determinate or statically indeterminate. So if the structure can be analyzed by use of equation of equilibrium, so that structure comes under the statically determinate structure. So first we have to see how many support reactions are there. Okay, two types of structures are there. The first one is statically determinate structure, another one is statically indeterminate structure. Compared to statically determinate structure, indeterminate structure is very stable because more number of support reactions are there. So now we have to identify whether this structure comes under determinate or indeterminate. So for that we should know about, so what is equation of equilibrium. So three types of equation of equilibrium is there. So already we know that is sum of horizontal force equal to 0, sum of vertical force equal to 0, sum of the moment about any point is equal to 0. So equilibrium means that is a stable condition. If the structure can be analyzed using equation of equilibrium, is known as statically determinate structure. Otherwise, if the number of unknown support reaction equal to equation of equilibrium, which means that type of structure comes under statically determinate structure. Example, simply supported beam, cantilever beam and 3-hinged arch. So next one, statically indeterminate structure. The structure which cannot be analyzed by using equation of equilibrium. So additionally we want one more equation based on the number of unknowns. So that equation is called as compatibility equation. So this type of structure comes under statically indeterminate structure. So for example, number of support reaction is 4, but equation of equilibrium is 3. We can easily find out 3 unknowns using equation of equilibrium. So one more unknown is there. We can't find out that one more unknown because we have to formulate at least 4 simultaneous equation to find out the 4 unknowns. But we are having 3 equilibrium equation only. So for finding one unknown, we want additional extra equation. That equation is called as compatibility equation. The example of indeterminate structure is fixed beam, fixed arch and continuous beam, etc. So basically the types of analysis is classified into 2 types. The one is types of force method of analysis. Another one is stiffness method of analysis. So first we will see about the force method of analysis. It is also called as flexibility method, compatibility method. So here unknowns are force. So finally we have to calculate the force here. So virtual work or unit load method, method of consistent deformation, 3-moment theorem, Castiglione's theorem of minimum strain energy, Maxwell's Morse equation, column analogy method and flexibility matrix method. So all this method comes under the force method. So all this method here the unknowns are only the force. So second method of analysis is displacement method. It is also called as stiffness method or equilibrium method. Slope deflection method, moment distribution method, Cunning's method, minimum potential energy method, stiffness matrix method. So this all the methods comes under the stiffness or displacement method of analysis. So in this all those methods, displacement of joints are taken as unknowns. Now we will see slope deflection method. Slope deflection method. So this method is ideally suited to the analysis of continuous beam and rigid jointed frames. So using this method, basic unknowns like slope and deflection of the joints we can determine. So first we will see about the assumptions. The first assumptions are all the joints are rigid. The angle between the two members does not change after the deformation also. So next one, the effect of axial force and shear force we can neglect. Only consider the effect of moment only. So these are all the assumptions. So we have to follow for the derivation of the slope deflection equation. So before seeing the derivation, first we should understand the sign convention. So always the sagging bending moment considered as a positive bending moment. So this is sagging bending moment, positive bending moment. So left side clockwise moment, right side anti-clockwise movement. So this type of bending considered as a positive bending moment. Another one is hogging bending moment. Left side anti-clockwise movement and right side clockwise movement. So this type of movement always produced negative bending moment. Positive bending moment, then negative bending moment. Okay, all the transverse load produce positive bending moment. Always end moments produce negative bending moment. So next one, coming to the shear force. While drawing the shear force, left side upward direction and right side downward direction considered as a positive shear force. positive shear force. So next sign convention, rotation. So always consider clockwise rotation as a positive and anti-clockwise rotation as a negative sign. So for example, so next one, sign convention for rotation, clockwise rotation. Clockwise rotation always consider as positive sign, positive sign. So next sign convention for a rotation. So clockwise rotation considered as a positive sign and anti-clockwise rotation considered as a negative sign. So this is a hinged support, here roller support, and here also hinged support. This is elastic curve. Draw the tangent line here. So the always arrow mark faces towards the tangent line. So this is A, this one is B, and this one is C. So here the rotation is theta A. Okay. Now draw the tangent line here. The arrow mark faced towards the tangent line. So here theta B. Okay. So here this is theta B dash, and here draw the tangent line here, here theta C. So now this is theta A. Theta A is clockwise rotation. Okay, so here positive sign. Now coming to theta B producing anti-clockwise rotation, so negative sign. Okay, theta B dash. So this is anti-clockwise rotation, so negative sign. Now coming to theta C, so this is producing clockwise rotation, so positive sign. So clockwise rotation considered as a positive sign, anti-clockwise rotation considered as a negative sign. So next one is settlement. So this is left side support, this is right side support. This is left side support and this one is right side support. So this is called as settlement delta. Okay. So the right side support is lower than the left side support. Consider delta as a positive sign. Okay. The right side support, here this is the right side support, this is left side support. The right side support is lower than the left side support. Consider delta as a positive sign. So next one. So after the settlement, the support comes here. This is before settlement, this is after settlement. So here this is left side and this one is right side. So here the left side support is lower than the right side support. So for this case we have to consider delta as negative. Okay. So the sign convention, clockwise rotation is positive, and for the settlement the right side support is lower than the left side support. Consider delta as a positive sign. So now we will see the slope deflection equation. Consider one continuous beam. This is A, this is B, A dash, and this support is B dash. So consider any arbitrary load. So it may be UDL, UVL and point load. Take at midspan. Take the midspan, span AB. So here the N moments will be developed due to the effect of external load, the effect of rotation of the joints and effect of settlement of the joints. So we have to consider only the N moments, because in the assumptions we have neglected the effect of axial force as well as the shear force. So here the N moments. So here internal moments are there, no? So here one internal moments are there, here one internal moments are there. So this internal moments, internal N moments is due to the external load. The first one is moments due to external load. Moments due to external load. Okay. And second one is moment due to the rotation. And third one is moment due to settlement of the support. So first we will see moment due to external load. The first one is moment due to external load. Due to external load, so some of the moment will be induced at the ends due to external load. External load may be UDL point load. So some of the moments will be developed at the end. So that is called as fixed end moments. So this is left side, this is right side. So fixed end moments M, F, A, B. Okay, this moment will be developed due to the external load at the left hand as well as the right hand. M of B, A. Okay, so M of A, B. So moment due to external load, F means fixed end moments. So here A, B means the first subscript denotes that the end moments, otherwise fixed end moment at A of the member AB. This is member AB. Moment at end A of the member AB. So here M of B, A means so fixed moment at end B of the member AB. So this is moment due to external load. And second one is moment due to rotation of the joints. Moment due to rotation of the joint. Moment due to rotation of the joints. So first we will allow the rotation at left end. Okay, this far end is fixed end, nearer end is hinged end, we have to consider. So allow the rotation here. If you allow the rotation, this is theta A, allow the rotation theta A. So due to this rotation, some of the moment will be developed at this end. Okay, so that is 4EI L theta A. Okay, so far end also some of the moment will be developed due to the rotation at the nearer end. So here 2EI divided by L theta A. So this is moment due to rotation of the joints. So due to this moment, some of the moment will be developed. So that moment is 4EI theta A divided by L. So for end, some of the moment will be developed due to the rotation at joint A. So here 2EI divided by L into theta A. So next one, so we have to allow the rotation. Third one, moment due to rotation of joint B. Okay, this is the far end. So allow the rotation here at joint B. So this is theta B. So due to this rotation, some of the moment will be developed. So this moment equal to 4EI divided by L theta B. So here the name of the rotation is theta B. So due to this rotation, some moment will be induced at the far end also. So that is 2EI L divided by theta B. So next one, moment due to settlement of the support. Moment due to settlement of support. Due to this settlement of the support, some of the moment will be induced here. Okay, the amount of moment equal to 6EI delta divided by L square. Okay, so same amount of moment will be developed at the far end also, that is 6EI delta divided by L square. Okay, so now we have to superimpose all the moments. So for finding the final end moment at A, so we have to sum up M of AB. What are the moments at end A? So in the first case, M of AB, we have to add this one. M of AB plus 4EA theta A divided by L plus 2EA theta B divided by L minus 6EA delta divided by L square. For finding the moments at n, we have to add all those moments. So if you want to find out the n moments at joint B. So we have to add this end moment M of BA and plus 2 EI divided by L theta A, then 4 EI L theta B, then 6 EI delta L square. So if we superimpose this one, we can get the final equation. That equation is called as slope deflection equation. So that is slope deflection equation at end A, MAB, the final end moment at A of the member AB equal to M of AB. This end moment due to external load plus 2 EI by L, 2 EI by L into 2 theta A plus theta B minus 3 delta divided by L. So already we have seen that due to external load, some of the moment will be developed at the end A, that is M of AB, due to rotation at end A, otherwise rotation at joint A, the 4 EI theta A divided by L moment will be developed. Due to rotation at joint B, some of the moment will be developed at joint A, that is 2 EI L into theta B. So this is due to the settlement of the support, that is 3 into 2, 6 EI delta divided by L square. So this is one of the slope deflection equation. So similarly, we can write other end also, that is MBA. Okay, MBA equal to MFBA plus 2 EI L 2 theta B plus theta A minus 3 delta divided by L. Okay, this is at the other end. So this is midspan. So here this is MAB end moment and this one is MBA end moment. Okay, so for each span we can write two slope deflection equation. So one at end A, another one at B. So this is the final end moments. These final end moments due to external load, due to the rotation at joint A and rotation at joint B, and due to settlement of the support. So these two equation is called as slope deflection equation. So this is a general equation. So this slope deflection equation so relates the moment fixed end moment as well as rotation and displacements. That's all. So we have to use these two equations while solving the problem. So we will see the one problem now. So analyze the two span continuous beam. Two span continuous beam. So one end is fixed and here this is roller support. Then another end is fixed. Here point load is acting at mid of this span AB, 40 kilonewton. Then so here this is 20 kilonewton per meter UDL load. So this is point A, here this is point B, this is point C. The span length is 2 meter. So here 6 meter. Then the moment of inertia is I, then here 2I. So this is the given beam. So we have to draw the shear force and bending moment using slope deflection method. Okay. So here number of steps are there. So first we will see the step 1. So before that we have to identify whether this structure is statically determinate or indeterminate. So already I have explained statically determinate structure means number of unknowns equal to number of equilibrium equation. Okay. So here statically indeterminate is equal to number of support reaction. So this is continuous beam. So we have to analyze using slope deflection method. So we have to draw the shear force as well as the bending moment diagram. So span AB having a point load, midpoint load 40 kilonewton is acting at 2 meter from the end A. Then span BC having 20 kilonewton per meter UDL load. So we have to calculate static indeterminacy. So static indeterminacy means a number of support reactions minus equation of equilibrium equation, that is the formula. So here always for the beam we have to neglect the axial deformation. So compared to the vertical deformation, okay, compared to the vertical deformation, this direction deformation is very less, so we have to neglect. Axial deformation is neglect for the B. Okay, so now SI statically indeterminacy equal to number of support reactions. How many support reactions are there? We have to calculate first. So here it is a fixed support. We have to neglect the horizontal support reactions. For the fixed support, number of support reaction is 2. For the roller support, number of support reaction is 1. This is fixed support, so number of support reaction is 2. So 2, 3, 4, 5. So total number of support reaction is 5. Equation of equilibrium, already we know that summation of H equal to 0, then summation of V equal to 0 and summation of moment equal to 0. Okay, so here also we have neglected the axial deformation H support reaction, so we can neglect here also. So total number of support reaction is 2, so 5 minus 2 equal to 3. Okay, SA is 3. Okay, so degree of freedom. Another one is, while solving the problem, we don't want this one, that is only for general knowledge. Kinematic indeterminacy, also it is called as a degree of freedom. Okay, so for the fixed support, the degree of freedom is 0. Okay, because there is no movement at the fixed support, because it has 3 support reaction. It does not allow any vertical movement, horizontal movement as well as rotation. The degree of freedom is 0. So coming to here, the degree of freedom is 1. Okay, so it does not allow any vertical movement, so only the rotation is possible. So already we have neglected the horizontal displacement, we don't want to consider that one. So here the rotation at B is there, the degree of freedom is 1. So similarly, this is a fixed support, the degree of freedom is 0. So here kinematic indeterminacy equal to 1, so that is theta B. Okay, so already we have seen the two types of method. One is force method of analysis, another one is stiffness method of analysis. So in the stiffness method of analysis, slope deflection method comes under the second category. Okay, so for the stiffness method of analysis, displacement of joints are unknowns. So for that we have to determine only the kinematic indeterminacy. Okay, so here theta B is unknown. Okay, so finally we have to calculate theta B here. So first step, the first step is fixed end moment. Fixed end moment. So we have to calculate the fixed end moment. So general formulas are there. So for the span AB, the first one is span A. Okay, span AB. Anti-clockwise moment will be developed at A and clockwise moment will be developed at B due to this external load. So if the beam is subjected to midpoint load, okay, the load is at mid M of AB. Fixed end moment at A of the member AB equal to minus WL divided by 8. So next one, M F B A. This also some of the moment will be induced due to this external load. So M of BA equal to fixed end moment at joint B of the member AB or BA. So here plus WL by 8. So left side always anti-clockwise direction and right side always clockwise direction. So some of the derivation also there. We don't want that one. So only we have to take the formula. So if the span is subjected to point load, left hand side, the formula is minus WL by 8, right hand side plus WL by 8. So here W equal to the intensity of the load 40. So minus 40 Here L equal to length of span AB only, that is 4 meter, divided by 8. So similarly here also W equal to minus 40 into 4 divided by 8. So finally we have to calculate the answer. Fixed end moment. So the answer is minus 20, here minus 20 kilonewton meter. The unit of moment kilonewton meter. So here plus 20 kilonewton meter. Okay. So next one we have to calculate the fixed end moment at B as well as C due to this UDL load. Due to this UDL load. For the span BC. So span BC is subjected to UDL load. Okay, if it is the UDL load, the fixed end moment at B, the formula equal to always left side anticlockwise moment minus WL square divided by 12 MF CB equal to plus WL square divided by 12. Okay, so here W equal to intensity of the UDL load. Intensity of the UDL load is 20. Here L equal to length of span BC, that is 6 meter, divided by 12 minus sign. Similarly here also plus 20 into 6 square divided by 12. So now we have to calculate the final answer. So what is the final answer? Final answer is here minus 60, then plus 60 kilonewton meter. Kilonewton meter. Here also kilonewton meter. The first step is find out the fixed end moments. Second step. So this is the second step. So for the second step, so we have to write down the slope deflection equation. Slope deflection equation. So for each span we can write two equations. So 4 equations we can write. So first we will write for the span AB. So for the span AB, MAB equal to M of AB plus 2 EI divided by L 2 theta A plus theta B minus 3 delta divided by L. This is the first equation at end A. Okay. End moment at A of the member AB. This is the general equation already we have derived. So here, so already fixed end moment already we have calculated. So in the previous one. So what is the fixed end moment? The fixed end moment here M of AB equal to minus 20 kilonewton meter. So next one theta A. Okay. So theta A means the end A is fixed support. So here there is no rotation at fixed support because the deflection will start from here, not here. Okay. So here there is no slope. Okay. So always at the fixed support the slope will be 0 value. Okay. So MFAB equal to minus 20 kilonewton meter already we have calculated plus 2E. So I also given for the span AB I equal to I value only divided by L means length of the span AB 4 meter into 2 times of theta A. So A is the fixed support. So the value is 0. So for the fixed support there is no slope. Okay, so it becomes 0. So theta B is the intermediate one. So the slope will come minus 3 delta by L. So in this problem, in the question itself, they didn't mention any settlement. If any settlement is given, we can substitute here. Otherwise, we don't want this term. So only theta B. If you simplify this equation, so finally we can get minus 20 plus 0.5 times of EI theta B. This is equation number 1. Minus 20 plus 0.5 EI theta b. This is equation number 1. So similarly, we have to write down the slope deflection equation for the span AB, but other end, that is MBA. Okay, MBA. Okay, MBA. So M of BA, I will write the equation, that is MFBA, okay, plus 2 EI by L to theta B. Here theta B plus theta A. We don't want delta because it is not given in the problem. So here end A is the fixed support. This term becomes 0. So if you substitute all the values, length of span AB and I of span AB and M of BE, already we have calculated plus 20. If you substitute all those values here, so finally we can get 20 plus EI theta B. So this is equation number 2. So this is for one span. So for the one span, we can write 2 equation. So now coming to the second span, that is BC. So for the BC also, we can write 2 equation, that is one at B, another one is at C. So MBC means final end moment at B of the member BC. So the equation is MFBC plus 2EI L, here 2 theta B plus theta C. We don't want delta term, delta C. So M of BC already we have calculated in the first step, that is minus 60, substitute minus 60 here, plus 2 E. So here I equal to 2I. Okay, the length of span BC equal to 6 meter, then 2 theta B. Okay, in the given problem at joint C is fixed support, so this terms also becomes 0. Okay, at the fixed support there is no slope, 0, that's all. If you simplify this one, minus 60 plus 1.33 EI theta B, this is third equation. Okay, so we can write one more equation, MCB at NC, that is M of CB plus 2EI divided by L, 2 theta C plus theta B, and C is fixed support, so this term becomes 0. So if you substitute M of CB value, length of span, BC value and I value, so finally we can get one equation, that is 60 plus 0.67 EI theta B. This is equation number 4. So now we are having 4 equation for the 2 span. For the 1 span we can write 2 equation, 2 span, total number of equation is 4. So these are all the equation. So we have to find out the unknowns here. In all the equation only one unknown is there, that is theta B. So theta B, rotation at joint B.